In 1919, the now famous Eddington expedition ventured out to see whether gravity can bend light, a major test of Einstein's general theory of relativity. By viewing a total solar eclipse, they showed that the sun did change the path of starlight, just as predicted, making Einstein and his theory world famous. Now, a whole century later, scientists have set out again to even more remote locations scattered across 4 continents. They will once more push the limits of astronomical knowledge, testing the same theory in a way Einstein could never have imagined. Their goal? To take a picture of a black hole, something so ambitious that it seemed impossible. Until now. The story of black holes begins as a puzzle. In 1915, Carl Schwarzschild noticed that Einstein's then new general theory of relativity predicted the existence of strange objects, known as singularities. They were places where his new equations describing gravity seemed to go haywire. Inside them was a bizarre place where time stopped and space became infinite. At the time, many scientists, including Einstein, considered them too strange to be worth seriously researching. Over the 100 years since then, however, evidence has piled up indicating that singularities do exist in our universe as black holes.
A black hole is the most mysterious object in the universe. It's when matter gets to be in such a small space and it's so dense that the force of gravity prevents even light from escaping. That's a one-way door from our universe.
We know they sit at the hearts of galaxies and they drive how those galaxies grow and how those galaxies die. They swallow gas and stars up. There are also these incredibly enigmatic and mysterious objects that live at the boundary between our 2 great theories of physics, general relativity, which describes gravity, and quantum mechanics, which describes the smallest things in the world.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe, and a black hole is that.
But observing this most extreme laboratory requires an extreme instrument. The immense gravity of black holes is an obstacle to viewing them directly. No light can escape from them, and they are tiny, crushing huge amounts of matter into small points of darkness. Even as the existence of these strangest of objects became more widely accepted, seeing them directly remained an impossible dream. In fact, to achieve the necessary resolution to see black holes directly, a single telescope would need to be the size of planet Earth, clearly too large to be feasible. Instead, astronomers spent decades studying the effects that black holes have on the matter around them. But the dream of getting more concrete evidence of these exotic objects was too tempting to be simply forgotten.
We all understand from a mathematical point of view that black holes exist, but to actually see something is a very visceral experience, and I think important for science and also for us to believe in it.
In the late 1960s, a new technique changed astronomy. Called Very Long Baseline Interferometry, it enabled several telescopes to observe as a team, creating a larger virtual telescope that could overcome constraints on telescope size. As this method spread, it became clear that direct imaging of a black hole was a real possibility. In 2009, the Event Horizon Telescope project, the E.H.T, was born to pursue this exciting goal.
The Event Horizon Telescope collaboration is a collaboration of scientists around the world from many different countries, continents and institutions to make a telescope the size of the Earth, giving us the highest resolution there is that currently is achievable with telescopes of any kind.
It was clear from the outset that the E.H.T would face unique hurdles. But seeing is believing, and the team was dedicated to revealing a black hole for the first time. To create it, 8 telescopes across the world were linked together. ESO plays a key role in 2 of these telescopes, both located on the Chajnantor Plateau in Chile. The Atacama Large Millimeter Submillimeter Array, ALMA. The other telescopes that make up the E.H.T are the IRAM 30-meter telescope in Spain, the Large Millimeter Telescope in Mexico, the Submillimeter Telescope in Arizona, the James Clerk Maxwell Telescope, and the Submillimeter Array both in Hawaii, and finally the South Pole Telescope in Antarctica. Together, they can achieve a resolution equivalent to reading a newspaper in Paris while sitting in New York. The immense challenges of the project soon became clear. The telescopes, all highly advanced instruments in their own right, were not built to work together. Making them work together as one interconnected interferometer required a huge team.
These are engineers, observers, theoreticians, and they all work together not only to image the event horizon of a black hole, but also to understand what we're seeing.
Very dry places at high altitudes are ideal for observations, since they avoid water vapor in the atmosphere interfering with the light from astronomical objects. After almost a decade of preparation, the E.H.T was finally ready to use all 8 telescopes as one instrument. On the 5th of April 2017, the E.H.T was for the first time aimed at the chosen target, M87 star, the black hole in the center of the enormous galaxy Messier 87, about 55 million light-years from Earth. Attempting to peer into the dark heart of a galaxy tens of millions of light-years away might seem like a strange choice. There are many black holes closer to home. But M87 star was carefully selected. It had 2 big advantages. It's one of the biggest black holes known, giving the astronomers a better chance of seeing it than smaller black holes in our neighborhood, and isn't too far north or south in the sky. Crucial if telescopes all over the world have to observe it at the same time. When those sleepless nights of observation ended, a new phase of work began. In order to find out what they'd seen, the scientists had to painstakingly combine and analyze the data. 2 computation centers, one in Europe and one in the US, combined a staggering quantity of data, about 350 terabytes per day from each telescope. The data had to be synchronized by atomic clocks, so precise that they lose only 1 second every 10 million years, and then transported on specialized helium-filled hard drives. Hand-carrying this precious cargo might seem like a low-tech solution, but the drives contained so much data that moving them by hand was, at times, the fastest data transmission in history. After countless hours of work on the data, an image began to take shape. This image would tell hundreds of scientists whether decades of work had attained the unattainable or had been in vain. Although black holes themselves are completely dark, they influence the path of photons traveling in their vicinity and leave an unmistakable signature on the light from the accretion disk surrounding the black hole, a large disk of matter gradually spiraling in towards its host. The infalling matter becomes very concentrated, causing friction to heat it to form a glowing plasma. The path of the light emitted by this glowing gas is determined by the black hole. The light passing close by it is bent by the enormous gravity skirting the edges, but light passing too close is captured, never to escape. Seen from Earth with radio telescopes, these effects manifest themselves as the shadow of a black hole. A dark central region silhouetted against the luminous plasma. After 2 years of painstaking calculations, the image was finally ready. Although taken from the staggering distance of 55 million light-years, the image revealed a ring-like structure with a dark central region. For the first time in history, the shadow of a black hole.
And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region. And you know immediately we're looking at an event horizon and a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
I mean, this is exactly what we had been looking for, but after 8 years and all that long process, a few weeks of imaging and they showed us exactly what we wanted. I couldn't believe it.
I have to say it's taken on a new importance now, as we actually have images that look like the simulations. So it's an extraordinary confluence between theory and experiment, and it promises tremendous breakthroughs on the horizon.
This historic achievement is a major milestone in our evolving understanding of the universe, and also sets a new precedent for global collaboration in scientific research.
One of the most uplifting things for me is the team that we've built and the fact that we're doing something that people have told us was impossible. And when you, at the end of the day, do something that people tell you you can't do, it's an incredible feeling. And I think the whole team is very, very proud that we've accomplished something like this. It's not just for us, it's for everyone.
As the E.H.T. is expanded, it will allow us to probe the deep questions that attract researchers to black holes. How well do our laws of physics hold up under the most extreme conditions we know of? How do the mechanics of gas, radiation and particles around a black hole work? Which theories are correct, and which will break down with more precise observations? Only time will tell which mysteries the E.H.T. will unravel next.